Hi, so here I'm going to give introduction to the course number theory. Today we're going to talk about what number theory is, give a short history of how number theory begins, and discuss some preliminary concepts that are needed in order for us to study number theory. So what is number theory? Number theory is the study of integers and integer valued function. According to Gauss, mathematics is the queen of science, while number theory is the queen of mathematics. So how does number theory begin? The first recorded literature about number theory is that of Pythagoras, and it's inscribed in the tiles of early civilization. Back in 1800 BC, Pythagoras give numerous solution to the equation a squared plus b squared is equal to c squared as the sides of a right triangle. This is now more commonly known as the Pythagorean triples. Fast forward to 300 BC, Euclid introduced his greatest common divisor algorithm, which is now known as the Euclidean algorithm. So it's an algorithm on how to find the greatest common divisors of two integers. Now, during the 300 common century, Diophantus' work on Arithmetica contains his workout problems in finding rational solutions to some system of polynomial equation. These are now more commonly known as the Diophantine equation. The work of Euclid and Diophantine started to spread outside Europe. So there are some record in history of mathematicians from India or China that give solutions to the equations that has been studied by Euclid and Diophantine. When 1600s come for math, communicate to other mathematicians several works on perfect numbers, amicable numbers, divisibility, and some Diophantine equations. One of the most famous equations studied by Fermat is the equation x to the n plus y to the n is equal to c to the n. And Fermat stated that for n greater than or equal to 3, this equation has no non-trivial integral solution. Unfortunately, Fermat did not give any proof for this equation. So he just claimed that he was able to find the proof, but stated that the margin on his notes are not enough to contain the proof. So this particular communication of Fermat to other mathematicians piqued the interest of Euler. And in 1700s, Euler proved most of Fermat's claims and started analytic number theory through his works on some of four squares, partitions, pentagonal numbers, and distribution of primes. But the major peak on the history of number theory is when Gauss aggregate and systemize the field of number theory. So through his work, Disquisitiones Arithmeticae, his most famous work is now known as the Fundamental Theorem of Arithmetic. Then from there on, it started to branch out into different field of number theory. So now we have elementary number theory, analytic number theory, so which is propagated by uh, Euler and Euclid. Algebraic number theory. So the algebraic number theory is a fusion of number theory and algebra. Diophantine geometry is a number theory finding solutions of Diophantine equations using graphs. Probabilistic number theory is a fusion between probability and number theory. Arithmetic combinatorics is a fusion between combinatorics and number theory. And then computational number theory. So usually computational number theory deals with cryptography and algorithm in finding solutions to equations, the Diophantine equations. For this course, we are going to discuss the following fundamental concept, just basic concept of sets, relations, and functions, number system, mathematical induction, pigeonhole principle, and binomial theorem. Next is divisibility in the set of integers. Here we're going to discuss division algorithm, greatest common divisor, Euclidean algorithm, least common multiple prime numbers, unique factorization theorem. After that, we're going to discuss congruence and congruence classes, modular arithmetic, linear congruences, Chinese remainder theorem, and application of congruences. We'll further discuss theorems on congruences like Fermat's Law theorem, Euclid's generalization, Wilson's theorem, Euler phi function, primitive roots and indices, powers, and roots. Then we're going to discuss finally quadratic reciprocity. Under this, we have quadratic residues, Legendre symbol, reciprocity law, arithmetic functions, Pythagorean triple. Now, for us to be able to smoothly go through this number theory, it's very important that we understand the language of the course. So, try to remember again some basic notation. So, we have here the symbol E, which is used as element. When you put a slash, so you're saying it's not an element. Okay. So yung baligtad naman na A, ang tawag natin dun is for all. And then yung baligtad na E, that's there exist. Okay. So the symbol C na may bar sa baba, that's the subset. Okay. So again, by definition, A is a subset of B. So again, by definition, A is a subset of B. If X is an element of A, then it should imply that X is an element of B as well. Now, the union of set is denoted by cup. So, A union B is the set containing all element X where X is either in A or in B. On the other hand, the intersection denoted as a cup. So, cup parang sombrero. Pabaliktad nung union. So, that's A intersection B is the set containing all X such that either X is in A and X is in B. Now, set complement is a backslash. So, pagka sinabing A, set complement B, or in other terminology, we use A minus B. So, that means all element X that are in A, but not in B. So, it's in A, but it's not in B. So, that's A minus B. Now, the Cartesian product is denoted by the multiplication symbol, the times symbol. So, A cross B is the set containing all ordered pair XY, where the first element X is from the first set A, and the second element Y is from the second set B. Okay. So, you're already familiar with this symbol. It's already introduced in your FCM course. Now, primarily the set that we're going to study is the set of integers. But let me go ahead and define the other set that may occasionally appear in our discussion. So the symbol N or the blackboard letter N, that's the set of natural numbers or counting numbers. So that's 1, 2, 3, and so on. The blackboard letter C is the set of integers. So that contains all the positive integers, the zero, and the negative integers. Q denotes the set of rational numbers. So rational numbers are quotient of two integers where the denominator is not zero. So that's m over n for all integers m and n such that n is not zero. So it's very important that n is not zero. On the other hand, q prime denotes the set of irrational numbers. So what are irrational numbers? These are non-terminating and non-repeating decimals. So there are two kinds of irrational numbers, an algebraic irrational number or a transcendental irrational number. When you say algebraic irrational numbers, these are irrational numbers that are solutions to algebraic equations. Like for example, square root of 2 is a solution of the equation x squared equals 2. So, yung solution nun is square root of 2. So, that's an example of an algebraic number. On the other hand, transcendental numbers are any irrationals that are not algebraic. For example, the irrational number e. So, it's not a solution of an algebraic equation. The trigonometric numbers, trigonometric values rather. So, those are transcendental numbers. Now, the set of real numbers is simply the union of the rationals and irrationals q prime. The symbol q prime means q prime is the complement of q with respect to the set of real numbers. So, a real number is either a rational number, or if it's not a rational number, then it's an irrational number. On the other hand, the set of complex number is the ordered pairs xy for all real number xy. But if you're not familiar with this representation of the complex numbers, maybe you're more familiar with the representation x plus iy, where I squared is equal to -1. That's the same. That's the same set. Okay, logical notation, when you say a double arrow, that means implies or if then statement. So for example, P double arrow Q is P implies Q. Now, the double-headed double arrow, that's biconditional or if and only if. So if you see P biconditional Q, that means P if and only if Q. So in logic, that means P implies Q and Q implies P. So as I've said, the focus of study of number theory is the set of integers. This is the course is precisely the study of the behavior, characteristic, and patterns of certain set of integers. Trivia first, C denotes the set of integers since the letter C stands for Zahlen. This is a German word for numbers. Usually kasi mga classical mathematicians are European, kaya and the most prominent language nun sa Europe ay German. So madalas yung mga symbols na ginagamit natin ngayon sa math, mga galing sa mga European mathematicians. Now, Q denotes the rational number, pero what does Q stand for? Q stand for quotient, actually. Q for quotient. Now, it's a rational number Pero bakit hindi R? Kasi yung R ay taken na already by the real numbers. Kaya hindi na nagamit yung R for rational numbers. Now, yung Q prime, the set of irrational numbers naman, so in set theory kasi, Q prime or prime, that the concept of putting a prime on a set means you're taking the complement of that set. So, Q prime simply means the complement of Q or the complement of the set of rational numbers, which is the irrational numbers. Okay. So, what we need to remember, which is already obvious to us, are the following properties of the set of integers. So I'm already assuming that you're already familiar with these properties. So let me just review them. First property is closure property. So that means that whenever you add or multiply two integers, the result is again an integer. So this is what we know as the closure property, or we say that the set of integers is closed under addition and under multiplication. Just a subset of the set of integers may or may not be closed under the operation addition and multiplication. For example, if we get the set of odd numbers, for instance. So let's take O to be the odd numbers. So you will see that if you get two odd number and you get the sum is not an odd number. For product, yes, the product is an odd number. So we say that the odd number is closed under multiplication, but it is not closed under addition, because when you add two odd numbers, diba, the result is an even integer. So that's what we mean by the closure property. Now, commutative property means that for every two integers a and b, the sum is commutative, meaning a plus b is equal to b plus a. So when you commute the position of a and b, the sum is still the same. The same goes for product. So a times b is equal to b times a. Again, not all operations on integers are commutative. For example, a minus b is not the same as b minus a. The same goes for division. A divided by b is not the same as b divided by a. But for addition, it is commutative for multiplication as well. Associativity property, for any three integers, we have a plus the quantity b plus c is the same as a plus b plus the quantity c, plus c. So what this means is that even if we change the grouping of the operation, the result is still the same for as long as we're only handling addition. Now, if the operation is only multiplication, it's also associative. So a times the group b times c is the same as the quantity a times b times c. So it doesn't matter where you put the grouping symbol. Having said that, that means that we can forgo or eliminate the grouping symbol all in all. And we can just have a plus b plus c. So no matter which group you add first, you still have the same answer. Now, on the other hand, if you have a mixed operation, let's say you have operations containing addition and multiplication, so the rule is the distributive property of multiplication over addition. So for any three numbers, if you have a times the quantity b plus c, so what you do is you distribute a on b and c. So you distribute a to b, so that's a times b, and then you distribute a to c, so that's a times c. And you proceed with the usual operation addition, so ab plus ac. The set of integers also contains what we call an additive identity. So the number 0 is called the additive identity, and the number 1 is called the multiplicative identity in the set of integers. So what does that mean? For the additive identity, it means that for any number a, if you add 0 to a, from the left or from the right. So a plus 0 is equal to 0 plus a is the same as a. It's called an identity because it doesn't change the value of a under addition. On the other hand, for multiplication, the identity is 1, which means if you have any number and you multiply it by 1, either from the left or from the right, so you have a times 1 or 1 times a, that's the same as a, meaning you did not change the value of a by multiplying the identity 1. On the other hand, we can also have what we call the inverse in integer. In group theory or in set theory, there are two kinds of inverse, the additive inverse and the multiplicative inverse. For the additive inverse, what it means is that for any integer a, there's another element which we denote by the negative of a. It's called the additive inverse of a, and it is that integer for which if you add it to a, the result becomes 0. So if you have a plus negative a or negative a plus a, then the result is 0. So parang siya yung nagka-cancel out ng value ng a. So yung inverse ng a is the integer for which babalik ka dun sa value 0 when you perform the operation addition. Kaya ang tawag sa kanya additive inverse. Now, on the other hand, a multiplicative inverse is that number that when you multiply to a, the result will become the multiplicative identity. In group theory, we denote this by a to the negative 1 or simply 1 over a. Now, unfortunately, in the set of integers, not every integer has a multiplicative inverse. Actually, the only integers that have multiplicative inverse are 1 and negative 1. When you multiply 1 to 1, the answer is 1. So that 1 is the multiplicative inverse of itself. When you multiply negative 1 to negative 1, the answer is also 1. So negative 1 is the multiplicative inverse of negative 1. Now, for any other integer, the multiplicative inverse is 1 over a. But 1 over a, unless a is 1, is not an integer. So that means in the set of integers doesn't have multiplicative inverse. Again, that's except for 1 and negative 1. For example, 2. 1 over 2 is not an integer. So 2 does not have a multiplicative inverse in C. Well, in a bigger set, for example, in Q, it has a multiplicative inverse. But since we're only talking of the set of integers as an element of the set of integers, it does not have a multiplicative inverse. C is a set containing an order relation. So the order relation is induced by the relation less than or greater than. So let A, B be two integers. The relation less than, which we denote by this symbol, is defined as follows. So the relation A is less than B is defined as, or we say that A is less than B if and only if B minus A is positive. So that means there is a positive number X such that B is equal to A plus X. So meaning in a way, parang sinasabi natin na mas maliit yung A kaysa kay B pag kailangan mo pang dagdagan si A ng X para maging equal sila ni B. Yan. So that's how we define less than. Now, pag sinabi mong A is less than B, then that means B is greater than A. So we can define the greater than relation using the less than relation. But if you want to state that as a property, so you say B is greater than A if B minus A is positive. Yeah. So that means na para masabi mo na ang B ay greater than A, kailangan idadagdagan mo pa ng X si A para maging equal sila ni B. Yeah. Okay? Now, another form of this relation is the less than or equal relation. So, we say that A is less than or equal to B, denoted by this symbol. So, parang less than na may equal sa baba. If and only if A is less than B or A is equal to B. On the other hand, yung counterpart naman na greater than, denoted by the symbol greater than, tapos may equal sa baba. So, we say that A is greater than or equal to B if and only if A is either greater than B or equal to B. So this less than relation induce an order in the set of integers. Because of this relation, the set of integers has the law of trichotomy. So what's the law of trichotomy? It says that given any two integers A and B, only one of the possibilities is true. Either A is less than B, A is equal to B, or A is greater than B. Well, anong ini-imply nun? So, if we look at the position of A and B in the number line, meaning, parang nagfo-fall in line sila. Sabi mo, okay, everyone fall in line, get in line, follow your height. So, ibig sabihin, yung smallest sa unahan, tapos papalaki. So, that's an ordering relation. So, that's the same kind of relation being followed by the set of integers because of the less than relation. So, dahil dito sa less than relation na to, there's a way to compare two integers A and B. So, pwede mong sabihin kung sino yung mas malaki or kung sino yung mas maliit sa dalawa or kung equal lang ba sila. So, because of that, you're able to position the smaller one on the left and the bigger one on the right. So, if A is less than B, so A is positioned on the left of B. If A is the same as B, of course, they are the same number. So, they are positioned at the same point. If A is greater than B, then A is on the right of B. So, parang pinapipila mo rin yung mga integers. So, that's what we mean by the order relation or order property. And this cause a total ordering. When you say total ordering, pwede mong ilinya lahat ng integers in a single file. Wherein, nakaayos na sila from increasing, from smallest to highest value. So the property provides the total ordering of the set of integers since for any two given integer, pwede mong sabihin na, oh, ikaw mas maliit ka, so ikaw sa kaliwa ka, ikaw sa kanan ka. So for example, you need to place 3. So hahanapin, pag i-compare mo si 3 sa mga integer na nakapila na. So for example, wala pa sa pila si 3, tapos nakita niya si 0, o 0. 0 is smaller than 3, so 3, punta ka sa kanan ni 0. Tapos nakita niya si 1. Oh, 1, are you smaller or greater than 3? So since mas malaki si 3, doon ka pa sa kanan ni 1, and so on and so forth. Until makita mo yung something na mas malaki kay 3, so stop ka na sa position mo. So, ganun yung nangyayari. You were able to order the integers exactly in a single line. And this line now is what we call the number line. Actually, the bigger set, the set of real numbers, is also an ordered set, meaning it also follow the trichotomy property. Yan. But again, for the purpose of the course, we're focusing on the set of integers. This property of the set of integers is called the well-ordering principle. Every non-empty set of positive integers has a least element. Ano sinasabi nun? Pag meron ka subset ng mga positive integers, so that's the set of natural numbers, then lagi kang may makikitang isang element doon. There exists a unique element in that set such that siya na yung pinakamaliit. Meaning, m is less than or equal to x for any other x in that set. Yan. For any other x is in that set. This property can be used to prove Archimedean property. So, ano ba yung Archimedean property? So, let A and B be two positive integers. Then there is a positive integer n such that n times A is greater than B. So basically, ang sinasabi nito, pag meron kang dalawang number A and B, you can multiply a big enough number on n para yung n times A mas malaki na sa B. So for example, yung A natin, let's say meron tayong number 2, tsaka 1,000. So, ang sinasabi nung Archimedean property, no matter how big the difference is, pwede akong mag-multiply ng n. So, I can find, there exists a value n such that if it's big enough, then the product becomes greater than b. Okay? For example, kung pipili ako ng n, let's say 100. So, we know that 2 times 100 is still less than 1,000. Tama? Kung 1,000, 2 times 1,000 is already greater than 1,000. So, yun yung sinasabi. So, that means I was able to find an n big enough so that when I multiply it to a, no matter how small a is, nagiging mas malaki na siya dun sa b. Okay? So, it's a very simple property. But later on, we'll find it very convenient. So, how do we show the Archimedean property? Ayan. So, parang sa atin, obvious na yung property. Pero, as a mathematician, of course, we want to always show in a general setting. Kasi, specific example lang yung 2 times tsaka 1,000. Pero, paano pag iba na yung value ng A? Paano pag iba na yung value ng B? Would the property still be true? So, pagka mga ganyang property, dapat pinapakita natin in a general setting. Of course, nagpapakita tayo ng certain example just to illustrate the property. But it doesn't actually mean na napuprove na natin yung property. Yun yung common misconception minsan pag nagpo-prove. Minsan, ang ginagawa lang ng student, it shows some specific example. Pero that doesn't necessarily apply in the general setting. Kasi baka mamaya, pag malalaki na yung number, baka hindi na totoo yung property. So, we always need to show it in general. Okay. So, ano gusto natin ipakita? Gusto natin ipakita that given A and B, makakakita tayo ng N such that NA is greater than or equal to B. So, yun yung kailangan natin. Kailangan natin mahanap yung N for any pair of AB. So, let's try to prove this by contradiction. Okay. In FCM, ano ibig sabihin ng contradiction? So, we assume the negative of the, or the negation of the statement, and then we find a contradiction. Okay. So, let's prove this. So, we're doing by negation or by contradiction. So, what do we need to assume? The conclusion is that there is an N such that N A is greater than or equal to B. So, let's assume the negation of that. So, suppose any integer n, so for all integer n, yung n times a laging mas maliit kaysa kay b. Okay. Kasi ang sabi natin dito, there exists. Kailangan makakakita ako ng n such that yung NA ay greater or equal to B. Ibig natin i-negate yan. So, ano negation ng there exists? For all. Ano negation ng less than or equal? Greater than or equal? Less than. So, let's assume that for all n greater than or equal, for all n in the set of natural numbers, the product NA is always less than B. The product NA is always less than B. Okay? Okay, so let's form the set. So, S to be the set N A, or rather gawin nating B minus NA. Yan. Okay. So, the set B minus NA. Well, kung B minus NA, ibig sabihin yan, mas malaki yan sa 0. Parang tinranspose mo dun yung, yan. Okay. So, anong ibig sabihin? The set containing B minus NA for all n in the set of natural numbers, yan, ay ano, laging positive. So, it's a subset of the set of natural number. Tama? Kasi sabi mo yung NA, mas maliit sa B. So, kung mas maliit yung NA sa B, by definition of the less than symbol, yung B minus NA, positive yun. Tama? So, S, which is composed of all these numbers, B minus NA, is a subset of the set of positive integers. So, by the well-ordering principle, ano sinasabi ng well-ordering principle? Ang sabi ng well-ordering principle, pag may subset ka ng positive integers, laging may least element. Yun yung sinasabi ng well-ordering principle, di ba? Pag may subset ka ng positive integers, lagi kang may least element. A least element always exists. Ano ibig sabihin ng least element? Yun yung M na lahat ng number sa set, siya yung pinakamaliit. So, M is less than or equal to any number in that set. So, sabi ni well-ordering principle, yung mga element ng S, meron dong isa na pinakamaliit. So, dapat makakakita tayo ng B minus MA, such that yung B minus MA na to, siya na yung pinakamaliit sa mga B minus NA for some M. Okay? Now, yung M na to, fix na to. Siya na yung magbibigay ng pinakamaliit na element na B minus MA. So, kung yung B minus MA, yung pinakamaliit na element, so this is what we call the least element. Then, kahit anong B minus NA, either less than or equal yon dun sa B minus MA. Now, observe natin yung element na B minus M plus 1 A. Di ba yung M plus 1 integer? So, yung B minus M plus 1 times A ay nasa S. Aha. Kasi, this is an integer. Iba, ano ba mga laman ng S? Lahat ng of the form B minus NA. So, this is an element of S. But if we simplify B minus MA, that's equal to B minus, by the distributive property, that's MA minus A. Tama? Okay. So, this is equal to quantity B minus MA minus A. Now, A is positive. B minus A is positive. So, anong ibig sabihin yan? Meron kang B minus A, binawasan mo ng A. So, anong nangyari? So, lumiit yung value. So, ang ibig sabihin, yung value na to, mas maliit yan, tama? Kaysa kay B minus MA. Mas maliit kasi binawasan mo ng A. So, yung B minus MA, pag binawasan mo ng A, liliit yung value ng B minus MA. So, mas maliit yon kaysa doon sa B minus M plus 1 A. Okay. So, looking at this, we now find a contradiction. Bakit? Sabi natin, ang B minus MA ay least element. Now, how can it be the least element if this is even smaller? is smaller than the least element. So that's a contradiction. Kasi kung least element ka, there should be nothing smaller than you, di ba? Pinakamalit ka na dapat. Kasi ikaw nga yung least element eh. Pero nakakita tayo ng member of the same set, nasa S din yan, di ba? Pareho silang nasa S, na mas maliit pa sa kanya. And that's a contradiction. That's absurd. So usually we write a lightning symbol when we find a contradiction to indicate that it is the contradiction that we're looking for. So if there's a contradiction, that means our supposition is false. So mali yung inassume natin. Kanina kasi sinupose natin, suppose for every n, na is less than b. So mali pala to. So this is false. Tama? So ano yung true kung false yan? O di ang true, so we therefore conclude that there exists an n, a natural number n, such that NA is greater than or equal to B. And that's what we want. Right? So, this is a very basic property which we'll find later na maraming property na true ang natural numbers or madali nating napapakitan yung property ng natural number nag-holds dahil sa Archimedean property na to. Which is again a direct implication of the well-ordering principle. So that's how important the principle is, the well-ordering principle. So always remember that the set of integers follow the well-ordering principle. Any subset of the positive integers has a least element. Okay? So, for the next discussion, we are going to discuss the principle of induction. That's another principle that is a direct implication of the well-ordering principle and which has a great tool in showing properties of the set of integers.